Howdy there, entomologists. Welcome to Kentucky Bugs. This week we're going to be looking at the ocular capabilities of our little friends. 518 million years ago, the Carrigmachella burst onto the Paleozoic scene off of the coasts of Greenland. It had complex eyes that could form rudimentary images. And then millions and millions of years later, their descendants became the arthropods that we know and love today with complex eyes. Most bugs, such as the praying mantis, have two types of eyes.
Hi there, I'm Jonathan, and this is Matilda the mantis. Wanted to show off Matilda's eyes here. Matilda and her other mantis friends are very famous for their triangular shaped heads, and then on each side of the head you will find the compound eye. These compound eyes are made up of hundreds, maybe even thousands of lenses depending on the species that all take their own individual picture. They then make a collage of these images with their eye.
These bugs also have a different type of eye called an ocellus.
Usually arrayed in a triangular pattern of 3 on a lot of things. Matilda here has those on top of her head. These help to perceive light and dark. They don't do a lot more complicated sort of visual information gathering than that.
Spiders, on the other hand, are different. They don't have compound eyes or ocelli.
Now this is Rosie. Rosie's a tarantula. She, like many other spiders, has a different kind of eye setup than what we see with the insects. In terms of spiders, we are going to see either a couple of rows of 3 or a couple of rows of 4. Most spiders have poor vision though. They don't really rely on it. There are exceptions like the jumping spiders that we featured in other videos.
Spiders such as hunting spiders and jumping spiders, however, have much better eyesight. These spiders attack from a distance, so it makes sense that they'd need more far-sighted vision to get to their prey.
But things like the tarantula, their eyes are quite small. If you look very closely on the top of her cephalothorax, then you can see them. She has a unibrow, unfortunately, some hair covering them up. And she doesn't really rely on these very much. She's more of a vibration sensor. They're very nearsighted. They don't rely on that sight very much. If she wanted to get that fixed, she would need a very specialized arachnid optometrist for that situation.
Now that we know how most bugs' eyes work, what are they actually seeing with them? By now, you probably have the idea that animals see the world differently. Snakes are sensitive to ultraviolet light or UV light, and some have heat-sensing pits on their face. Birds are very sensitive to UV light, and it can be a direct signal to them of what they are seeing. We humans see in a visual wavelength of 400 nanometers to 700 nanometers, also known as the visual spectrum. UV light, on the other hand, ranges from 10 to 400 nanometers, so unfortunately we can't see it. But we aren't talking about these vertebrate villains. We're here to talk about our backboneless buddies. Insects are sensitive in a range of ultraviolet light to red light. When looking at the spectrum, we see where humans range within that nice 400 to 700 spot. Now we compare that with the sight of a bug. And since optometrists refuse to see bugs for eye exams, scientists have created experiments in order to see how bugs view the world. In 1941, as World War II is raging, some dudes named Weiss, Sorachi, and McCoy pondered the idea of what bugs can see and tested it on beetles. So the beetles got together and about 60% of them reacted positively to light between 365 and 528 nanometers in length. The light in this range can be described as violet blue, blue, and blue-green. A few of the beetles, however, were also attracted to longer wavelengths, such as orange-red and infrared. So now, armed with our tested idea that we found in the lab, let's see how it works in the field. Behavioral studies suggest that bees and butterflies use UV patterns in the sky for orientation and navigation, a lot like how sailors would use stars for navigation. But their sights are not just set on the sky, they're also looking below for flowers and plants. When bees are out looking for nectar, their most likely attractants in plants are purple, violet, and blue. However, that's just what we see. Bees can look through a field of white flowers, and at super speeds they are able to hone in on, land, and drink the nectar of flowers due to their UV emissions. So something will look like this to you or I, but it will look like this to a bee. But flowers aren't the only things that give bugs direction. Many bugs forage at twilight when blue light dominates the spectrum of the sky. Have you ever wondered why moths and other bugs are attracted to your lamps outside? It's because they're adapted to using the blue light it's giving off to find out where they need to go. That's like if your GPS just drove you around in circles and you decide to follow it. Think of that next time you plug in your bug zapper. If you're having issues with a bunch of bugs outside your house crowding your lights, try switching to a warmer light color in order to not attract the critters. Special thanks to Luna's Bug Cafe for letting me take videos of their moths. Also, if you're wearing a headlamp and being bugged to no end, try using the red setting that they won't notice. And don't be discouraged that you're missing out on the wonderful UV world that bugs can see because I might have lied to you earlier. That's right, a study conducted at the University of Georgia suggests that young people can detect an isolated UV peak at 315 nanometers. So next time you're outside, think of the wonderful, beautiful, invisible world that insects are seeing, but don't forget to wear sunscreen. Thank you all so much for watching. We'll have a new video up next Wednesday. If you're bugging for more content, make sure to check out our other social media accounts. We'll have videos coming out on there throughout the week. Lastly, what do you call a really old ant? An ant's eek. Thank you very much.